16 week or 17 week, or in some of them still 18 weeks. Okay, so and it depends on our clothes. Okay, so I just wondering that because today is the 12th, right? So we should be able to finish today. Okay, and let's take 2 weeks for you guys to presentation. Okay, so should be 26. Should be able to finish. Okay, so how about we have the final exam on the January of 2? Is that okay? The January 2 will be 17 week, right? 17 week. Or you guys want to postpone? Yeah, the first, you don't want to postpone?
I want.
You want to postpone? Yeah, anyway. So which will be good? Second. Or just raise your hand. Yeah. Okay. Second. Second. Hold on. Second. Second. 1, 2, 3, 4, 5, 6, 7, 8. And 9, right? 9.
Final exam.
9. 9. What about 9? No? 2. You want a 9? 3. And nobody else? You have the majority in the first week. But of course, you still can prepare one slide, one A4 size. Yeah. So 2 is okay because 2 is the majority. Okay, it's okay. 2, okay. So January 2, okay. January 2. Okay, here we have shown some comparison. Okay, so this is a quite good example to show you if insertion and desertion. Okay, CNT in titanium dioxide. Okay, can be also used in the insertion. So usually for the insertion and desertion, there's a low capacity. Unless CNT has a high, okay, because CNT has a high surface to volume ratio, and here is the conversion as alloying, okay, de-alloying and alloying has a usually higher order, higher theoretical capacity compared to the insertion. And conversion, yeah, more stable, yeah, usually has a high capacity, okay, more stable, and also I would say some of the materials because it's a metal oxide, so also low cost, okay, and environmental compatibility, okay. So this is just for you said reference. So and the most important is the nano size, okay, the nano size because the nano size can help the morphology to represent the key feature, okay, capacity of leading this innovation of material from being theoretical capacity. So anyway, nano size is quite important because if we can prepare such materials can be small size, okay, small size that will be more surface to volume ratio to making the leasing can be suffer more area to accommodate charge and discharge, okay. So that's why here is another slide to show the nanostructural materials. Because the nanostructural materials can have their advantage. It looks like here. Okay. Active material has a high surface to volume ratio. Okay. Therefore, they can intensify. Okay, intensify the active site. So therefore, you have more and more active site. Okay. And high surface area imply high contact area. Okay. With the electrolytes. Because usually you have the electrolyte right here. And you have the cathode side. You have the anode side. Anode. So to make it the electrolytes immersed to the anode and cathode is quite important because the contact area, I would say the contact area, the electrolytes can be, can be immersed inside of the nanostructure, okay, the nanostructure. So you can provide more reaction, okay, reaction. So high contact area is electrolytes. Therefore, you can lead it to the high lithium ion flux, okay? Across lithium ion, you can have a high flux. Transfer, okay, high lithium ion transfer process. And therefore, you can infuse into the diffusion, the lithium diffusion, okay, enhance the power capacity. So actually now, the active materials has nanotechnology. There's a lot of application using the nanotechnology. Silicon, we already discussed about that many times. Here, we wanted to emphasize about the silicon. Silicon has a lot of application for the solar cell, right? And the chip, right? Semiconductor chip. And for the lithium battery, silicon is also abundant because they have a high solid capacity. And the formation is lithium 22 and silicon 5. Okay. Volumetric. Okay, volumetric capacity even higher. Okay, this one and this one is similar. Okay, so you can say 9,000 over 9,000 and 700. This is per square. Okay, cubic. Okay, and here is per gram. Okay, per gram. That's the difference. Okay, depends on the unit. Okay, depends on the unit. And the graphite is charge potential of the silicon almost close to the graphite, 0.4 voltage. Okay, 0.4 voltage. And this is very unfortunately it's 400. Okay, quite high. Why the silicon is most commercialized? Because silicon is cheap, and then we have a lot of the application of the silicon ingot, right? Last time we had talked about single crystal silicon, right? Single crystal silicon. So single crystal silicon, you have to cut, right? And during cutting, actually there is some of the particle, right? Silicon particle lost, right? Silicon particle lost. So we can correct those particles to use the battery, right? And also polycrystal as well. Polycrystal. Polycrystal. polycrystal silicon. Polycrystal silicon, because if we wanted to use silicon for lithium-ion battery, actually we don't need to worry about that, we need the 6N or 9N or 12N, right? You only need to consider about the purity, because for the battery application, yeah, actually 99.9 is quite high, right? But for this kind of the silicon, right, it can reach 6N, even 12N for solar cell, right? For solar cell. So those particles we can correct, high purity silicon particle we can correct for use the lithium-ion battery. So that's why there's a quite commercial popular application using the silicon. Okay, but unfortunately, because there's a particle light. So if I ask you guys, can you prepare porous silicon? Porous silicon is quite important if we want to apply to the lithium-ion battery. Because we want to accommodate, if now, this is a silicon particle, right? If you can prepare like a needle-like silicon, right? Silicon. Which means you have some area. This is some area you can accommodate the volume expansion, right? Or I would say have some of particle inside as a pores, right? Pores. So therefore, even the volume expansion, right? Still, you can, because inside has some space can accommodate the volume expansion, right? So some of the research they do in such yolk shield. The yolk shield. This yolk shield is outside is silicon dioxide, inside is a silicon. Okay, and then this is a soluble silicon right here, and then outside is the SiO2. And here is pores. Okay. It's a pores. So you can see to making there's some space to making the silicon volume expansion, right? Volume expansion. So still, the silicon dioxide is fixed here. Okay, fixed here. So still, this is quite good. As I see, this has been published in some Nature. Okay, Nature. They have some methodology. Okay, some methodology can do. Okay, like etching process. Okay, like some etching process can do. For example, the first cycle, you can have a silicon particle, right? Silicon particle, and then you can coating silicon with the metal, some of the metal, okay? And then silicon this is metal. This is the metal. And outside coating SiO2. And then etching. We're making a metal etching. So inside has a silicon, and then you have outside has a shear, SiO2. You can use some of the NaOH or the S, okay? some of the sodium hydroxide, something like that, to etching inside of the metal, right? So the metal will be empty, right? So you can release the metal, and then here is the force. Some of the process, okay, some of the process you can do. So in mostly research are trying to avoid the volume expansion of the silicon. Okay. You can the text you can read by yourself. Okay. Let's look about this diagram. This is the silicon. Okay. And then dissociation silicon doesn't mean the charge. Okay. This is image. So therefore, you have to expand, right? And during discharge, because outside here is SEI, right? It's a SEI. So once charge and discharge, you can see the SEI will bigger and bigger, bigger and bigger. Finally, you get this thicker SEI, many cycles. You get a thicker SEI, right? So the thicker SEI to making this difficult to charge again. Okay, charge again. Okay, so let's look at the button side. So this study elements that the electrical contact between the active side and both conductive carbon and the current collector undergo a drop due to large volume expansion and contraction of the silicon anode. Okay, so therefore this will lead irreversible, cannot reversible. Okay, reversible. This is because of the cycling lifetime fading. Fading doesn't mean fail. Okay, capacity fail. Okay, because of the thicker SEI after many cycle. So that's because of the electrolytes will always react with the surface of the silicon. So we are careful about the thickness of this lithium silicon. Okay, surface reaction. This surface reaction we call the interfacial reaction. Okay, interfacial. So we have to be very careful to monitor about this thickness. Okay, this thickness. So some of the nanostructure, nanotechnology, we have to do. Usually for bulk, like a particle-like, because usually have the solid. So you have no choice that the SEI will become bigger and bigger, right? But nanotube should be okay. Here, I want to show you about silicon nanowire to overcome this challenge, okay? Because the particle-like, you have no choice. It is solid. Particle-like, that means it's solid, right? So you always get a thicker and thicker, thicker and thicker, right? So to do such a method, it is quite hard because you have to coat in the metal and then coat in the SL2 and then etch. So you have to do a lot of procedure, right? If you want to do a lot of procedure, although you success, but the price getting high, right? And then you have no competition, right? Your product will become the low competition. So some nanostructure you have to consideration. So research focus on to making the change in layer morphology, such as nanowire, tube, nanospeed, okay, are considered due to their capacity provide necessary free volume for accommodate the silicon to expansion, right? Because the nanowire and nanotube, you can see here. Here is quite good. This is nanowire, and they can do inside actually is the nanotube, silicon nanotube, right? By using some of the methodology like the chemical solution or some of the thermal evaporation, okay, thermal evaporation. So you can see charge and discharge here is a 600 cycle. Oh, sorry, 6,000 cycle. charge discharge always maintain cooling efficiency maintains 90%, right? You can see the first cycle is right here, 600, right? 600. Okay. Of course, compared to a cylindrical capacity, is still low. But anyway, we wanted to see about the long term. You can see here is always maintained, right? Quite good, right? This is quite good. So this evidence that the nanotube and nanowire can provide high efficiency of the charge and discharge, high performance of the charge and discharge. Okay. And this is another idea. Okay, idea that what about we mixture together? If you cannot make in the nanowire, right? Looks like such perfect morphology. Can we use some soft materials and solid materials? Like carbon. Carbon is quite soft, right? Carbon is quite soft. And silicon. So this is the carbon-based materials, right? Carbon-based materials mixed with the silicon, okay, as the electrode. Okay, so inside there's a carbon and silicon, carbon and silicon. So you can take both advantage, okay? Take both advantage of the carbon and silicon, because the silicon has high cylindrical capacity. So inside you can look about, for example, this is a carbon matrix, right? And then inside you mix with silicon particle, right here. Okay. So because the carbon is soft, so you can maintain the free volume expansion, right? Free volume expansion. And carbon as a graphite, right? So IC6, right? And silicon can I22 Si5, right? Si5. Right, so they can take both advantage. So you can see this is the literature. Okay, you can see the cycle is quite good. Okay, cycle. Okay, regarding the graphite, there is three kinds of the graphite. Non-graphite. Okay, non-graphite. Non-graphite actually is the microstructure looks like that. There's a random. Okay, there's a random. And then second is a graphite. Graphite is looks like a perfect layer by layer, stacking together. It quite looks like a array-like. Okay, so they can just like if you using a tap, 3M tap, you can peel one layer, second layer, 3 layer. Okay, so we call this is also soft graphite. Soft. So usually this kind of the materials we call the soft graphite, which can accommodate this charge and discharge quite well. But here, non-graphite is poor because it is quite mechanical. Because it is random arrangement, so it is quite hot. Okay, quite hot. Hot is hot graphite. Okay. The mechanical strong, it's quite strong. So this in transfer is quite bad. There is a poor transfer. And there is a partially graphite, okay, partially, just in between, okay, just in between. So let's look at about this three kind of mechanism. Here, soft carbon, that means the soft graphite, okay, here, okay. Soft. And then, graphite, hard carbon is right here. Hard carbon is right here, okay. And then partial graphite is a soft. It's a soft, okay, soft. And here, graphite is right here, okay, here is graphite. Sorry, please change it. This is soft, okay, soft. That means in between, okay, in between. And graphite, okay, is partial, okay. soft graphite. Okay. Soft graphite is partial. Okay. Is that okay? This is the partial graphite. Okay. Partial graphite. And this is graphite. And if we look at about this is by color. Okay. Red color is the hard carbon. Okay. And then blue color is the soft carbon. Okay? And then dark color is right here, is a graphite. Can you see some difference? Uptake, that means this in discharge and charge. Okay? Discharge and charge. So as you can see, once this in release, okay, this in release, okay, that's mean this in out, okay. Actually, the cylindrical capacity, if we look at about here, this in uptake discharge here, it's cannot reverse to the zero, right? So you only have this charge and discharge. Once they discharge, you can see not all the leasing charge out. Now, that means all the leasing should be released, should be uptake, discharged out. But there's not every leasing. So-called some of the leasing has been stuck inside. Do you understand? Been stuck inside. So therefore you can see, once they discharge, so cannot reverse to the zero. Right? This is the hard carbon. Because the hard carbon, you know, the leasing cannot really transfer in and out, in and out. Okay, so you get this curve. Is that okay? So now, if we use some of the materials like soft carbon, it becomes better. Okay, become better because soft carbon is in between both graphite and hard carbon because they have a slightly arrangement. So it is better to make in the leasing accommodate in and out, right? So you can see, oh, here is much better, okay, much better. But if we look about here, perfect graphite, right? It is become charge and discharge. You can see there's 100% can be released, okay. So for the soft carbon, it's also almost 100% can be released, okay. But cylindrical capacity is slightly different because the materials graphite has a difference. Okay, even the same materials, you still can see charge and discharge. You can see the capacity is quite low here. The blue color capacity is around reach 300, but here for the graphite is mostly reach 400. Okay, graphite can reach 400. But in between, soft carbon is just even less. Okay, so you can see the graphite is more better, right? The graphite is more better because they have the high capacity, specific capacity, and also mostly can be charged and discharged. They can fully recover. Do you understand? So you have to look at about this point. Although, okay, the hard carbon has a high capacity, but you can see it cannot fully recover. Okay, fully recover. So the better will be this one. Okay, this one. Graphite. Okay, 400 capacity, and then they can fully release. Is that okay? Okay. So this is we call it disorder correction of the small graphite grain. Okay, which is originating in the presence of the nanovoids. Okay. And CNT, okay, also much better than carbon. CNT is a major ingredient is for the carbon. So you can see CNT can accommodate LiC2. Okay, and there is a SW CNT or multi-wall CNT, MW CNT. So CNT exists due to their superior unique conductivity is quite good. mechanical thermostat is also quite good. Okay, so there's a high theoretical capacity. Okay, because you can see it is also quite there. If you have a multi-layer, so you have one layer, second layer, three layer, so you have more space to accommodate this thing. Okay, and it is quite stable. And we call this as quite active site, high active site. Okay. And titanium dioxide is also one of the quite famous materials because the titanium dioxide, the titanium active materials show very interesting. Okay, and the volume expansion because there is a low taxility. Okay, doesn't mean there is a eco-friendly. Okay, eco-friendly, and then low volume expansion, just only 2 to 3%. Okay, only 2 to 3%. So that's quite good. So on both of the leasing charge and discharge, it shows excellent. But compared to the capacity is quite low, similar to carbon. Okay, similar to carbon, 175 to 330. Okay, and no electrical conductivity because it is quite looks like an insulator compared to the carbon. The conductivity is poor. Okay, conductivity is poor. So people, because this kind of the materials is able to produce nanostructure, nanopowder, titanium dioxide. So it is not quite technology. Technology-wise, is actually is quite is able to reach because technology is not require complicated. Okay, technology it is quite easy to fabricate nanostructure of titanium dioxide. So how the titanium dioxide is stable? Because you can see the titanium dioxide has a tetrahedral. Here is the tetrahedral structure. Okay, and then they can transfer in. Here you can see here is a lithium. Okay, so actually, if you look at about the yellow color, the red color is right here. This is the oxygen. Okay, this is oxygen, and here is the titanium. So inside is this is the tetrahedral structure, 八面体 tetrahedral structure, and then once the lithium transfer inside of the tetrahedral structure, it's quite stable. Okay, because the lithium transfer it can accommodate to the center point. Okay, center point. So therefore, it can maintain quite stable. Tetrahedral structure is a TiO6 tetrahedral. Okay, tetrahedral. So lithium atoms are placed in the middle of the window, form TiO6 tetrahedral. Okay, tetrahedral. So there is a four-fold of the panel coordinate. So you have a lot of you can see here. This is the unicell, TiO6 unicell. So there's many space can make the lithium to transfer it. Okay, to lithium to transfer inside of the tetrahedral. So therefore, it can maintain quite stable. Okay, and then the best one is the less volume expansion, just 2 to 3%. So therefore, this kind of the material will be quite stable. That means you can use it for a long time. You know, I have one experience to buy a battery, backup the battery, and then as I remember, I just charged few times maybe. I don't use the backup batteries quite frequently. Just maybe as I remember 1 to 3 times, and when I travel to the United States, as I remember, I just use less than 10 times, not used quite frequently. So I put in my store, and then after 1 year, I put it back. I see, whoa, my battery become bigger. Yeah, I never used just only 1 year, and I used less than 10 times. Actually, and then this battery become bigger. And then when I wanted to charge, I feel is that okay or not? Because already it's bad, right? Already it's bad. Maybe it's dangerous. But I try to charge again. It cannot use it. So actually, you still have to consider about the cost. So if the materials can suffer for a long time, right? And it is quite important because the cost may be low, right? So if you want to making the device can suffer for a long time, charge and discharge has a less volume expansion. It's quite important. Okay. So people they starting like to mixture, okay? Because you are the material science, you can do whatever you can do like graphene mixed with TR2 nanotube. Okay, because TR2 nanotube, it just looks like you prepare silicon nanowire, silicon nanotube. You also can prepare titanium oxide nanotube. Yeah, you can prepare by electrical chemical process, 电化学合成方法. Electrical chemical process, you can synthesize the nanotube. And this nanotube mixed with the graphene. Because in the previous slide, we talked about titanium dioxide is a poor ionic conductivity, right? Transfer, the conductivity is poor. But you mixture with the graphene. Graphene is a high, the conductivity is quite high, right? So therefore, graphene can support titanium dioxide to make a high electron transfer, right? And TR2 accommodate the charge and discharge quite stable, right? So those can take both good advantage. So you can see they can suffer quite high. You can see here is there's a capacity. Okay, it's quite high. Okay, quite high. And this is the cycle. This is just some of the reference. Okay, some of the reference. Of course, right now I believe there's a lot of the research, maybe even better than titanium dioxide. Okay, and tin dioxide also similar to TR2. Okay, because the tin dioxide and the TR2, okay, is a quite similar structure. Okay, quite similar structure. SNO2 has a cylindrical capacity. Okay, SNO2 cylindrical capacity can storage about 8,000. Okay, 8,000, which is more twice than graphene. Better, even better. Okay, so this is also one of the materials that we can select to create nanostructure. This is flake-like. Okay, flake-like. Flake-like, you can see like you can provide more surface to volume ratio. Okay, so charge and discharge is quite good. Okay, charge and discharge. If we want to look at about the capacity as a cycle number, you have to look at about the performance. If here is the charge, it's a dark, okay, and then discharge is the blank. So you can see charge and discharge mostly has the same capacity. That means quite good, okay. And then you can use the high rate. High rate doesn't mean the high current density charge and discharge. If a high current density charge and discharge, capacity will become low. Low current density charge and discharge, capacity will be high. Do you understand what I mean? Which means the C rate. High current density charge and discharge, that means you can charge it very fast. Current is high, but current will be high, the capacity become low. Just looks like if you want to transfer something from this room to another room, if we want to fast, okay, fast transfer, and it cannot fully to transfer. If we slowly to transfer from one room to another room, and then we can completely transfer this room's matter to another room. Do you understand? So-called now, if here, there's a table right here, right? Table right here. And there's a 16 table right here. If I ask you guys, okay, 1 minute, please transfer this 16 table to another room. Just only 1 minute. And you guys will be, okay, 1 minute, 1 minute. Okay, transfer. And maybe only just 60% table be transferred to another room. But if I ask, okay, 1 hour, please transfer. 16 table to another room, and you can completely transfer this table to another room. So this is what we call a rate. Okay, we call it rate. If you have the higher rate, okay, higher rate, you get the lower capacity. Okay, you get the lower rate, okay, you get a higher capacity. Okay, higher capacity. This is similar to when you charge the electrical car. Okay, if you want to charge the electrical car faster, you can have the less capacity. Okay, less capacity. So-called Tesla car. If you want to charge within 1 hour, okay, within 1 hour you can maybe at 80% capacity can reach. But if you just charge 10 minutes, you maybe just 30% capacity can reach. Do you understand? Okay, it depends on the rate. Okay. So last point is the solid state electrolyte. Solid state, because solid state electrolyte is also quite important in the big topic, but because the time limitation and I just wanted to show you, okay, about some idea. Okay, because of the solid state device is quite important. Usually there's a liquid state right here. So there's a small separator, it's quite thin. So listen in and out, and you can see here it's easy to penetrate. Okay, the dendrite growth and then to penetrate. So therefore both sides will get shock. 导电, okay, will get shock. Okay, contact each other. But if we apply solid electrolytes, which means not liquid, use the solid. So even dendrite growth, okay, and then still here is a solid. So it will be difficult to penetrate. Okay, difficult to penetrate. So we call this a solid state device. Okay, solid state. And this is our previous work. Okay, we utilize porous SiO2. Okay, porous SiO2, as I mentioned previously, do you remember? Porous SiO2 has rice husk, okay, as a porous SiO2. And then as you can see, here is an XPS measurement. There's an orange bar. Orange bar, that means you have the surface orange. SiO2, porous. And there's orange. Because there's a pore. Okay, pores. And we use this to mixture some of the polymer materials. Just wanted to make it a thin film-like, to have a bendable. Okay, to bendable. Why we need the bendable? For example, this is okay. Usually you have the cathode side, you have the anode side, right? If both sides of the cathode anode can bend it, including inside of the separator, is bendable. That means that your batteries can be bending, right? Right? So you can be, even you bend it, the mechanical is quite strong, right? So therefore it is quite important to making the inside separator should be bendable. Right? Because the bendable can make this contact. Here you can see the color. The electrolyte is immersed into the cathode and anode, right? So they can fully to mixture with the cathode and anode. So bending is quite important. Here, right? The materials and bending is quite important. So you cannot make it this film too solid. Too solid will be not flexible. Looks like that. For example, you have, for example here, you use the plastic, okay? Okay, use the separator. And then this is the cathode, and this is the anode, right? And it cannot bend, right? It cannot bend. So therefore, inside here, the separator also cannot fully contact to the both sides of the anode and cathode, right? That's the point. So to making this thing, I would say easy to making this thing. It's quite easy. You can use the plastic, right? You just use the plastic and then drop to the electrolytes, and then you have the solid state electrolytes. But the problem is that you cannot fully mix each other of both spin. That's the point, right? So to making this thing electrolytes is good enough, bendable, and then weighting is quite good. The weighting is quite good. That means this thing should be good weighting with the cathode. And this thing, separator, also good weighting with another. For both sides of the cathode and anode is quite important. Is that okay? Right? So that's a challenge. Okay? The point is that you have to make this kind of, that means, oh, here it should be good weighting. If you have a poor weighting, okay, you have a poor weighting, even you have the solid state device, that's very poor. I would say, the solid state device is very safety, all right? Even you just shake it and then drop to the ground, you still safe. You cannot explode. But you know, this thing is hard to transfer, so that's a poor performance. So you cannot make the safe device, but poor performance. Then nobody want to buy it. Okay, so. This is our study that we use the mixture materials using the polymer, because the polymer is soft, soft enough, and the mixture with the SiO2. So therefore here is a SiO2 structure. It is a channel-like, like a channel-like. But they provide OH bond. Okay, OH bond. And OH bond is a negative, negative, negative. Okay? So therefore, this thing can transfer to here. Okay? This thing can transfer to here through this bond. This is our theoretical calculation. You can just skip it. Okay? So here we have to calculate about the MSD. MSD is the mean squared, mean MEN squared. Distance. Displacement, sorry. Just like a mean free path, okay? That means the average transfer distance. So average transfer distance, when we modulate 5% of the SiO2, okay? 5%, add the 5% of the SiO2, we get a higher MSD, okay? You may ask me, Professor, you told me that the SiO2 has such porous can transfer these things, but how come maybe we can add more and more SiO2, and then you have more opportunity to making the distance transfer? But how come we add 20% and then it becomes drop? Because too much SiO2, right? Too much SiO2 still will, become black. You cannot use too much. So sometimes the median is okay. Okay, if you want to have a step, okay, median, always get the median, not way down, not the row, right? Something like that. The median will be better. So this is the mechanism. At what time? We have almost. Okay, just finish. Okay, this is the PEO. So PEO is a polystyrene oxide. Okay, this is a crystallinity. So actually, we mix these polymer materials with the SiO2. Okay, so we can produce a bendable solid state electrolyte, and it is quite soft and sticky. You know the sticky, 黏黏的. Because the sticky can make it, if your fin has a sticky, you can make this fin easy to mixture with the anode and cathode. Okay, you cannot make the fin too strong. If too strong, no sticky, and then it is hard to make an electron transfer. Okay, so you have to make the fin sticky. Okay, but if the fin too sticky, that means you cannot become a solid to transfer for operation. Okay, so this is our cylindrical calculation. Yeah, we get the higher conductivity at 5% here at the room temperature. Ideal conductivity can mostly reach about 110 times -4. Okay. So this is a C-rate charge, as I mentioned. Okay, this is the 1C, and then when we increase the charge rate, that means the current density. If you increase the current density charge, capacity will be low, right? But if we reduce the charge rate, still can maintain quite the same. Capacity can reach the 1,000. Okay, 1,000. So this is quite reversible. Okay, you can see reversible. Okay, this is the rate C rate. That means the current density charge, as I mentioned before, right? Current density. If you have a higher charge rate, you have the lower capacity, right? Low charge rate, high capacity, and high charge rate, low capacity. Okay, so yeah, so this is the voltage output, and you can light it. Okay. Yeah, so this is the final slide. Okay, so we still have time. Okay, let's take a break and let's take a break. We have.